My name is Zhang. I'm from Carnegie Mellon University. Today I'll be talking about this project called Electrick, where we use electric field tomography to enable low-cost touch sensing. This work has been done with my colleague, Gierad, and my advisor, Chris Harrison. So as we all know that touch interaction is popular, but traditional touch screen technologies are well suited for only flat and small applications such as our phones and tablets. There are many everyday objects with irregular surfaces, such as tools and toys, where traditional touch screen technologies will not work, or too expensive to large surfaces, such as walls and furniture. Previous research has looked into adding touch sensing into everyday surfaces. The most intuitive way is to use camera with computer vision to track our fingers. It is also possible to use capacitive sensing to detect the coupling between our hand and the conductive objects. Finally, acoustic sensing, either passive or active, has also been explored in previous work. There is also a growing body of research which aims to add interactivity to rapidly prototyped objects. These techniques can allow a designer to prototype both form factor and the interactivity. Previous work has embedded electronic components into prototyped objects. With special 3D printers, it is also possible to print optic channels and conductive traces for touch sensing. And finally, we can also use external sensors such as copper patches and cameras. From this related work, we can extract several ideal properties for a touch sensing technique. First, it has to be versatile so that it can work on objects with irregular surfaces. Also, it should be inexpensive to scale to large surfaces and ideally easy to apply. In this work, we introduce Electrick, which enables versatile touch sensing on everyday surfaces and objects, such as tables, toys, and tools. Electrick is low cost, which creates touch-sensitive area under $1 per square foot. Our technique can also be applied with so many fabrication methods. Let me show you one way we made this. We first spray a conductive coating. Then we add 8 copper electrodes. Now we are adding a green top coat, but this is optional. With Electrick, this object then becomes interactive. It can detect discrete touch locations and perform a coarse touch tracking. Now let me show you a live demo of 2 objects. So the first one is a spray-painted steering wheel right here, and the second one is a single material 3D printed bongo game. So we printed out of a slightly conductive filament. I will cover this material later on. So let's see. So here is the steering wheel. With Electrick, we can detect different touch locations. Also, on the wheel, you can do swipe right, left, right, touch, no touch. And also for the bongo game, here, as you can see, the bongo is right here. I can detect touch locations like 1, 2, 3, and 4. And even multi-touch is possible, like 1 and 2, 2 and 3, 1, 4, 2 and 3. Just to clarify, this is not a very expensive filament. We bought it on Amazon under $50. And other than these electrodes underneath the bottom, as you can see, it's just a piece of static plastic. So that's my live demo. Thanks. Also, this year, we'll be demoing Electrick at a demo session, so please stop by and play around with these demos. Now, let me talk about how it works. Our sensing principle is based on the shunting effect, where a grounded object, such as the user's finger, will shunt a fraction of the current from the electric field to ground. This shunting effect has been widely used. One example is our capacitive touch screens. More similar to our method is airborne electric field tomography, which was first explored by Smith in his seminal thesis work. And finally, another similar approach, electrical impedance tomography, was recently explored in our previous work. In this project, we constrained the electric field in a conductive coating, instrumented with electrodes on the edge. Here is an illustration of electrodes with only 8 electrodes. We first insert a current through a pair of adjacent electrodes. To probe the electric field distribution, we measure the voltage from all other adjacent pairs of the electrodes. As I said, when the finger touches on the panel, a fraction of the current is shunted to the ground. This will cause a localized voltage drop. Now, to increase the resolution, we can rotate the current emitting pair and the voltage measuring pair. This will give us a mesh of cross-sectional measurements. Now, using tomography, we can recover the electric field distribution inside that panel. Here is a real-world demonstration of our sensing principle. On the screen, we show the reconstructed electric field. In this case, we indicate the low current density with blue. Now we can use blob tracking to track where the touch happens. Now, let's talk about how we implemented the system. Here you can see our circuit. Let me talk about some interesting pieces. First, we have an ARM Cortex-M4 microcontroller with built-in ADCs. Next is the signal generator, which created the excitation signals. And then we use 4 multiplexers to multiplex the excitation signal and the ADC channels. The board then sends the data to a laptop, which runs machine learning models to calculate touch locations. Just some quick specs on the sensing. So the excitation signal is 200 kilohertz. Our ADC samples at 4 megahertz. We collect 200 data points for an RMS calculation per measurement, and each measurement takes roughly 137 microseconds. This gives us FPS at roughly 180 with this 8 electrode setup. We run a user study to evaluate Electrick. For the time being, let me share with you some high-level results, but please refer to the paper for more detail. We tested 5 different design factors of interest: number of electrodes, different size of surfaces, different conductive material, 3 surface geometries, and different isolated top coating on top of those conductive materials. And our procedure used an evaluation template with a 4x4 grid to guide participant touches. We first train our system with 1 round of training. Note that we only use the data collected from the 4 corners of this grid to train our regression models to prevent overfitting. Then we performed 3 rounds of testing. In total, we collected over 13,000 of data points. Of course, all these results were collected live. Across all the conditions we tested, Electrick was around 99% accuracy at segmenting the touch and no-touch events. Touch tracking distance error was under 1 centimeter on average. Let me talk about more specific findings. So we tested 8, 16, and 32 electrode counts using this one test panel, but with the number of electrodes used controlled by a software. Here you can see the touch plots from all participants with 2 sigma ellipses. Interestingly, 16 seemed to do the best. The results suggest that Electrick does not require a large number of electrodes to work well. Then we test 3 different sizes with these evaluation templates. The result indicates that Electrick performs well across different sizes. We also tested Electrick with 3 materials, which I will talk about in a minute. The result indicates the velostat, which is one of the material, yields better accuracies. This is because velostat is more homogeneous than the other 2 materials. It is linear, it has more linear signals that can be better captured by the model. This result also suggests that for the other 2 materials, we probably need a more controlled coating process and more calibrating point rather than these 4 points on the corners. For geometries and coating tests, we found no significant differences between all these conditions, except for the paper coating, which might be a little bit too thick for capacitive coupling to pass through. Ideally, a sensing approach can be trained with a small number of users and work for all. We did a leave one out test to evaluate cross-user accuracy. The result indicates no significant difference from per-user accuracies. This suggests that Electrick allows a walk-up usage where a user do not have to train the system before he or she uses it. Electrick works with a wide range of materials and fabrication processes. As I mentioned before, conductive materials can be coated on the surface. We can also use them as the structural material. Our technique works with a wide range of resistance. Let me first talk about some solid materials that are compatible with our technique. First is the velostat, which is a carbon-loaded plastic form, often used for electronic components packaging. So it can be laminated onto thermoformable sheet for vacuum forming. Here, we made a phone case with velostat. Now being touch sensitive, it can detect different grasping gestures for quick launch of applications, like this camera. We can also stick velostat to flat surfaces, in this case, the top side of a controller. Now we can switch between different templates to get different interactivities. This could allow, for example, a designer to test different designs quickly, or a game developer to offer a custom controller. There's also conductive ABS, which is sold in form of pellets and also filament. Here we mold a toy out of these pellets, which shows that Electrick is compatible with widely used industrial manufacture processes, such as injection molding. In this example, we 3D printed a Bungo Hero game with only one material, which is the conductive ABS, and attached electrodes to the bottom side of it. With Electrick, this previously static object now becomes interactive. You can use the electrode, you can see the electrode along the bottom, but otherwise, it's just one piece of static plastic. Many pliable materials can also work with Electrick. For example, we can mold a toy out of conductive silicon. Because Electric is inexpensive, it makes it feasible to enable touch interactions on many low-cost toys. We also made a jello brain with Electric.
The frontal lobe plays a large role in voluntary movement. The occipital lobe is the visual processing center of the mammalian brain.
Play-Doh is also conductive. In this example, we can create an interactive snowman.
I'm melting! I'm melting!
Finally, Electric can be painted or sprayed on almost any surfaces. We use carbon conductive coatings which we bought on Amazon. With this material, we can spray or brush paint many objects, including those with irregular surfaces. I've already shown you the steering wheel example, so here I'm going to show you another one. We spray an electric guitar and turn the top surface to be a touchpad. Now a user can customize where he wants the controls to be for the sound effect. For example, he can turn on the electric guitar effect by pressing the toggle button. Or adjust the wah-wah effect with a slider. This is just one example, but you can imagine with Electric, a user can custom control on almost anything, for example, like a door, a refrigerator, or a wall in this case. We can toggle the light on and off, or adjust the brightness by sliding up and down. As many other electric field sensing approaches, Electric has limitations. One common question we get about this technique is the durability of the coating. We actually found the material we tested quite durable. For example, there's no detectable damage on our testing panels at the end of the evaluation after 10,000 plus touches. We did see, however, that EMI from fluorescent light can affect the reported touch location. So electromagnetic interference might be an issue. We also find that certain extreme grounding conditions can affect the signal. And finally, our technique is not high resolution enough for the multi-touch, but we are currently working on this problem. Finally, we'll be holding a demo today and tomorrow. Please stop by and try them out. Thank you. I'm happy to answer questions. Hey, Daniel.
Hi, Daniel Ashbrook from the Rochester Institute of Technology. I wonder if you could talk a little bit more about the machine learning that is required for your system to work.
Yes. So for the machine learning, we have a classifier that classifies whether there's a touch happen on the panel. That's for touch and no touch detection. We have two regression models, one for x-axis and one for y-axis. Yeah.
And what kind of training has to go into that?
So for all the testings, evaluations that we run in the user study, we train the regression models on the four touches on the four corners. And then that's all a user needs to train the system to work on that touch panel. And for the classifier, we first train the system with 30 data points when the user is not touching the touch panel, and then train all the touch points as label them as touch events to train the classifier.
What about complex objects like your steering wheel?
Yeah, it's the same thing. So before this presentation, actually, I got here and then trained this steering wheel by touching different locations. You can train the radius or different degrees and feed them into the regression model.
Okay. Yeah, thanks.
No problem.
Hi, this is Koho from Purdue University. Very good. So I have a quick question. Can you share a little bit more detail on how do you decide the electrode placement?
How to design the electrode
placement? Like
placement.
Right now, you are. It seems you are doing the evenly. Can you share a little bit more rationale?
Yes. So in the exploration, we found if you distribute the electrode evenly and under the bottom side, like this bongo game, it will give us a more linear signal that's easier for machine learning model to train. But since machine learning is good at learning the differences and the signature in the signal, it can actually compensate for, even if you don't put the electrodes so evenly spread out, machine learning can still capture that. This is actually one of the primary reasons why we use machine learning to learn the touch, is to compensate for the variance in the fabrication. One of the variants is the electrode's displacement. So it doesn't have to be super evenly spread out.
Okay, thanks.
Hi, I'm Mike from Google. Really appreciated the work. I was very curious about the power that was required to do this and grounding condition changes. So I couldn't tell from the videos if you were running with your laptop plugged in or not, and does the model compensate for that?
So that's a good question. For the power consumption, it's just for now, the current implementation is roughly 120 milliamp because we didn't optimize in that direction. That's why it's basically another touch screen. You can think of it as another power consumption for the touch screen. And for the grounding condition, because some extreme grounding condition could be, for example, if I bongo accidentally touch this grounding plane, because unlike a touch screen, right, it's just flat on top of the phone. If you go with this complex geometry, there's so many grounding conditions can happen. For example, if I touch my laptop, because the object itself is so complicated. So sometimes it can happen. And also in the demo, you can see we actually powered the laptop because we found if the laptop is powered, it can give us a more significant shunting point because it completes half of the grounding loop. But actually, it does not require the laptop to be always plugged in. In the demo section, actually you can try. I will not plug in my laptop and then still works. Cool.
Thank you.
Cool.
And one last quick question. Okay. This is Zhang from Gierad. So it seems like you have two classifiers. I'm wondering, like, the first classifier to recognize touch versus non-touch. Is that possible? Like, you use some other methods or build a user-independent model to recognize touch versus non-touch?
Yeah.
Right, so because when touching, non-touching, probably the signal is very different from each other.
Yes, exactly. So actually, we actually offload this problem by machine learning. But when we explore with this technology, we actually found that the signal change is very significant. You can see the raw data if you come by you stop by the demo section, you can see the signal changes significantly. And also, if I use the classifier, it's still cross-user, so actually verify the cross-user accuracy is good. So it does not have to be a heuristic model for it to work across user. It can be a machine learning. A global classifier can happen.
Cool. Thank you.
All right, so let's thank Yang once